ever wondered what's really going on when you flip a light switch? Or, plug in your phone, even something huge like lightning. It's way more than just saying electricity. We're talking these invisible forces interacting all the time, pretty much running our modern world. So today we're doing a deep dive into the three big ones, the fundamental building blocks for any electrical circuit: current, voltage, and resistance. And these aren't just like abstract science terms. They're the actual language of how power works. Why wires are different sizes, why circuit breakers trip, all of that. Our mission today to kind of demystify these things, understand how they connect, maybe in surprising ways, and really equip you to see the electrical world a bit differently. And we've been digging into the Electrician 2024 AIT Curriculum Guide, which honestly lays this stuff out really clearly, very
Cool.
practical. Okay, let's unpack this. So let's start with current. We hear that word all the time, right? But electrically speaking, what is an electric current? What's the basic idea?
Right. So at its heart, electric current is simply the flow of charge. Specifically, it's usually free electrons moving along. Think of them going from a place with lots of extra electrons, that's the negative source, towards a place that's missing electrons, the positive source. And for this flow to happen, you really need three things. You need that electric field, kind of the push, you need those free electrons ready to move, and crucially, a clear path for them, that path. That's what we call a conductor.
Okay, conductor, like a wire, basically.
Exactly. And the source material gives a good analogy. Think of a fully inflated tire, puncture it, air flows out. It wants to equalize the pressure. The hole is like the conductor. Make the hole bigger, a better conductor, and the air equalizes faster. A battery is kind of similar with its charges. Once they equalize, the battery's, well, dead. Current stops.
That tire analogy really clicks. Equalization. Okay, so lightning is the big dramatic version.
Oh, absolutely. Huge, rapid equalization of charge buildup in clouds.
Right. But what about something less dramatic, like, say, in our phones?
Mm-hmm.
There's current flowing there constantly, right? But it feels totally different from lightning.
That's a great point. It is totally different in scale and control, but the principle's the same. Lightning is this massive, uncontrolled surge inside your phone's microchips. You've got these incredibly tiny controlled currents, precise flows of electrons carrying information, not just raw power. Every tap, every calculation depends on these minuscule managed currents flowing through complex circuits. Same idea, electron flow, just vastly different scale and purpose.
Tiny control flows. Makes sense. So whether it's a lightning bolt or microchip signal, we're talking flow. How do we actually measure this invisible movement? Put a number on it.
Good question. That's where we get into quantities and units. First up is electric charge itself. We use the symbol Q. And the unit for charge is the coulomb. We write it as C. Now, a coulomb, it's not just one electron. It's a truly staggering number. We're talking roughly 6.24 times 10 to the 18th electrons.
Wow. That's almost impossible to picture. Quintillions.
Exactly. Gives you a sense of scale. Then we measure the flow of that charge. That's electric current, symbol I. And its unit is the ampere, or just A. An ampere tells you the rate, how much charge is moving past a point per second. The math is pretty straightforward. Current I equals quantity of charge, Q, divided by time, so I equal
Yeah.
T, which means 1 ampere is exactly 1 coulomb of charge flowing past a point every single second.
Okay, so it's not just that it flows, but the rate, how much per second?
Ampere?
Amperes. Got it. That precision feels important. Now, something I've heard debated, the direction of flow. Does electricity go from positive to negative or negative to positive? It seems like a point of confusion.
Yeah, that's a bit of a historical quirk. Way back, before electrons were even discovered, scientists kind of arbitrarily decided current flowed from positive to negative. That's called conventional flow, sometimes whole flow.
Okay.
But then, once they discovered the electron, they realized the actual charge carriers, these negative electrons, were physically moving from the negative terminal to the positive one. That's electron flow,
So conventional was the guess. Electron flow is the reality.
pretty much. And confusingly, both terms are still used.
Yeah.
It often depends on the field. Engineering might use conventional. Physics might focus on electron flow. But for our purposes today, and in the guide we're using, we're sticking with electron flow. Negative to positive. Think of those little electrons moving toward the positive side. That's our picture of current.
Right, negative to positive. That simplifies things for us here. Okay, so current is the flow, electrons moving. But what makes them move? You mentioned an electric field, a push. Is that voltage?
Exactly. That push is voltage. Think of it as an imbalance, a difference in charge between 2 points. Imagine one atom loses an electron, it becomes positive. Another atom nearby gains one, it becomes negative. Now you've got this tension between them, an electric field, a potential difference. That potential difference is voltage.
So it's like electrical pressure.
That's a great way to think of it, yeah. Electrical pressure. Consider a car battery. The chemical reactions inside basically strip electrons from one terminal, making it positive, and pile them up on the other, making it negative. That creates a voltage between the two posts, and that's key. Voltage is always measured between two different points. It's a comparison.
Always between 2 points.
Okay.
Like measuring the height difference between 2 points on a hill, not just the height of 1 point.
Perfect analogy.
Yeah.
And that pressure, or height difference, is what drives the current, pushes those electrons along the conductor.
But going back to the tire, the flow stops when the pressure equalizes. How do we keep that electrical pressure up? Keep the current flowing continuously in a circuit?
Right. That requires something to maintain the difference. That's electromotive force, or EMF. EMF is the force that actively keeps that charge separated, that keeps replenishing the pressure, ensuring the current doesn't just flow once and stop. It's the pump in the system.
Okay, EMF, electromotive force. Is that measured in volts too?
Yes, it is. The symbol for EMF is E, and the unit is the volt, V. So a 10-volt battery provides an electromotive force, E equals 10V. And, for a practical circuit, you need that source of EMF, the battery, the generator, whatever. You need the conductors, the path, and you need a load.
The load. That's the thing, using the electricity, like a light bulb.
Exactly. The light bulb, the motor, your phone charger, that's the load. Without all three, source, path, load, connected properly, you have an incomplete circuit and no current flows.
Source, path, load. Got it. So what actually creates this EMF? Where does this push come from? You mentioned batteries and generators. Are there other ways?
Oh, yes. It's actually quite diverse.
Yeah.
The source material lays out 6 main ways we can generate EMF, create that voltage. 1, magnetic. That's your big power plant generators and alternators, moving wires through magnetic fields.
Okay, the main way we get grid power.
All right. 2, chemical. That's batteries and fuel cells. Chemical reactions producing voltage. Very common. 3, friction. Static electricity. Rubbing things together. Lightning is a massive example of this. Charge separation through friction in clouds.
Like shuffling your feet on the carpet?
Exactly. 4, heat. This is called the thermoelectric effect. Join 2 different metals, heat one junction, cool the other, you get a small voltage. Thermocouples use this maybe to sense a pilot light in a furnace.
Interesting. Okay, what else?
5, pressure. This is the piezoelectric effect. Squeeze certain crystals and they generate a voltage. Some barbecue lighters use this. You click the button, it hits a crystal, makes a spark.
Wow, I never knew that's how those worked. Cool. And the last one?
6, light. Photovoltaic effect.
Yeah.
Solar cells. Light striking specific materials knocks electrons loose, creating EMF, directly converting light to electricity.
That list is amazing. Magnetic, chemical, friction, heat, pressure, light. It really shows how fundamental this force is, appearing in so many ways.
It really does.
Yeah.
From huge power plants down to a tiny lighter spark or a solar panel. It's all about creating that initial charge separation, that potential difference.
Yeah. Now, speaking of voltage, I noticed in the source, sometimes it uses the symbol E and sometimes V. You said E is for EMF. So what's V for? Is there a difference?
Yes, there's a subtle but important distinction, especially when analyzing circuits. E is generally reserved for the source voltage, the electromotive force itself. Think of it as the total push available from the battery or generator. We often call this a voltage rise.
Okay, E is the source, the rise.
V, on the other hand, usually with a subscript like VLOAD1 or VR1, represents the voltage across a specific component or load within the circuit. It's the amount of electrical pressure being used up or dropped by that component as current flows through it. So we call this a voltage drop.
Ah, drop versus rise. That makes sense.
Yeah, and sometimes you'll see double subscripts like VAB, meaning the voltage specifically between point A and point B in the circuit. But the key is E for the source's total push, V for the voltage used by a part of the circuit.
Okay, that clarifies that. So we have the push voltage, E or V. We have the flow current. But you mentioned nothing's perfect. There's always some opposition. What's that third piece?
That would be resistance. Symbol R, resistance is basically the opposition that a material naturally offers to the flow of current. It's a property that actively hinders those electrons trying to move through.
So it's like electrical friction.
That's a very good way to put it. Electrical friction. It depends on the material structure, essentially how easily its electrons can be knocked free and move along. Materials like copper, silver, gold, they have lots of easily freed electrons. They don't put up much of a fight. They're good conductors, meaning they have low resistance.
Right.
Then you have materials like glass, rubber, plastic. Their electrons are held very tightly. They strongly resist current flow. They're poor conductors or good insulators. They have high resistance.
So conductors have low resistance, insulators have high resistance. Does everything have some resistance then? Even copper wire?
In the real world, yes. Pretty much everything has some resistance. Even the best conductors like copper offer a tiny bit of opposition. It might be very, very small, but it's there. Superconductors are a special case, but for everyday circuits, assume some resistance.
Okay, and the unit for this resistance?
The unit is the ohm, named after Georg Ohm. The symbol is the Greek letter omega.
Yeah.
So if you see R equals 40A, that means 40 ohms of resistance.
And that zigzag line in diagrams, that's a resistor.
Exactly. That symbol visually represents a component designed to have a specific amount of resistance opposing the current flow.
Perfect. Okay, we've met the stars. Current I, voltage E, resistance R, flow, push, opposition. Now, how do they all relate? Is there a rule, a law that connects them?
There absolutely is, and it's probably the most fundamental law in basic electricity. Ohm's law. Ohm figured out the relationship. He stated that the current flowing in a circuit is directly proportional to the voltage applied and inversely proportional to the resistance.
Directly proportional to voltage, inversely proportional to resistance.
Yep. The equation itself is beautifully simple. I equals voltage divided by resistance.
IER.
Okay. This one equation explains so much about how circuits behave. It's the key relationship.
So let's break down those proportionalities. Directly proportional to voltage. What does that mean practically?
It means if you keep the resistance the same and you increase the voltage, the push, the current, the flow, will also increase proportionally. More push, more flow.
Like turning up the pressure on a hose.
Exactly. If you double the voltage E, you double the current, assuming resistance R doesn't change.
Okay. And the other part, inversely proportional to resistance?
That means if you keep the voltage the same, but you increase the resistance, the opposition, the current will decrease. More opposition, less flow.
Like pinching the hose.
Perfect analogy. If you double the resistance, you cut the current I in half, assuming the voltage E stays constant. So the water analogy holds up really well here. Voltage is the pump pressure, current is the water flow rate. Resistance is how narrow or constricted the pipe is. Ohm's law just puts that relationship into mathematical terms.
That makes it very clear. More pressure, more flow. More constriction, less flow. Why is knowing this specific law, Ohm's law, so vital? Not just for electricians, but for understanding our tech world.
Because it allows prediction and control. It's not just descriptive, it's predictive. If you know how much push you have, voltage, and how much opposition there is, resistance, you can calculate exactly how much flow current you'll get. This is crucial for designing safe systems. You need to know the current to choose the right wire size so it doesn't overheat. You need it to select the correct fuse or circuit breaker to protect the circuit and prevent fires.
Ah, safety. That
Yeah.
makes sense.
Absolutely. It's also essential for troubleshooting. If a device isn't working, measuring voltage, current, or resistance and comparing it to what Ohm's law predicts can tell you where the problem lies. Is the voltage too low? Is the resistance too high? It's the foundation for diagnosing electrical issues.
So it's a practical tool, not just theory. How do people actually use it day to day? Like, how do they apply that IER formula?
Constantly. The power of Ohm's law is that if you know any two of those three values, voltage, current, resistance, you can always find the third one just by rearranging the formula.
Okay, so you don't always have to solve for current.
Nope. The three common forms are to find current, I, it's IE's ER. To find voltage, E, you rearrange it to E equals IXR, current times resistance. And to find resistance, R, it's RE's EI, voltage divided by current.
IER, EIR, RRZI.
Exactly. And there's even a little visual aid some people use, the Ohm's law triangle. It helps you remember which formula to use. You just cover up the value you want to find.
A triangle aid, okay. Can you give a quick example, like just the setup?
Sure, let's say you measure the voltage across a heating element as 120 volts. E yields 120 V, and you know its resistance is 40 ohms. R yields 40. Using Ohm's law, IAER, you calculate the current. I yields 120 V 40A, which equals 3 amperes. So you know 3 amps will flow through it.
Okay, straightforward.
Or say you measure 2 amps, I yields 2A flowing through a resistor. You know the resistor is 30 ohms. I equals 30. You want the voltage drop across it. You use EUIXR. So E equals 2A, 30 equals 60 volts. That resistor is dropping 60 volts.
Got it.
One more. You have a 10-volt source, EL's 10V, and you measure 5 amps of current, I equals 5A flowing. What's the total resistance of the circuit? Use R, EI, EEI. So R equals 10V, 5A equals 2 ohms. The circuit resistance is 2 ohms. See, knowing any two lets you nail down the third. It's fundamental for checking if circuits are operating as designed safely.
That really shows how practical it is. Prediction, calculation, safety. It all comes back to this relationship. What an incredible deep dive. We've really unpacked these core concepts: current, voltage, resistance, and the law connecting them. It feels like going from just seeing the light switch to understanding the hidden mechanics behind it.
It truly is the bedrock. Understanding this relationship between the push, voltage, the flow, current, and the opposition,
Yeah.
resistance, helps make sense of so much. Why safety codes demand certain wire sizes, why different devices draw different amounts of power, how fuses protect things. It all comes back to these principles. It's empowering knowledge, really.
Absolutely. So now that you, our listener, have this clearer picture, the push, the flow, the opposition, think about something common like a toaster or maybe a hairdryer. We know resistance creates heat. How do those appliances intentionally use high resistance? And what could go wrong if that resistance was, say, too low or maybe way too high? What system in your daily life, now that you know about these invisible forces, will you look at with, well, a completely new perspective?